Welcome, this is Wireless Future. I'm Erik Larsson and I'm here today as always with my colleague Emil Björnsson. Hello Emil.
Hello Erik, how are you today?
Good Emil. How are you this morning?
Great. So what episode is it?
Yeah, I just realized today is episode 50. 50.
Wow. I didn't expect that when we started.
No, I never expected we would get so far. So for how many years we've been recording now? This is like the 5th year or the 6th year?
I think we are approaching later this year that it has been 6 years since the first recording. So that's amazing.
Yeah, but the episode 50 I think is worth celebrating. So it becomes something like the 50th, not the 50th anniversary, but the 50th episode anniversary. Is that a word like that? No. Yeah, so it's catching up, I think, with our age. I mean, it did catch up with your age, didn't it? Already some time ago, and it's now soon catching up with mine.
Yeah.
Yeah.
So let's see how long we keep going. But I thought that, of course, one of the challenges with running a podcast for a while is to find topics that we haven't covered before and talk about them, or, of course, going back to topics after a few years. But I think we have managed to find a topic that we haven't covered so far for this anniversary.
Oh, totally. So today we're going to talk about satellite communications.
Yes, we will leave Earth and move into space.
Yeah, into space. And that's something where me personally, I have not really worked at all, but you, Emil, have a bit. So what is satellite? What's new in satellite communications? I mean, we got TV broadcasting for decades.
Yeah.
So what's happening now with the mobile communications with satellites?
Yeah, so we certainly have had satellite communication for TV broadcasting, as you said, for decades, 50, 60 years even. And there, the idea is that you put a satellite at a particular altitude above Earth. So it's 36,000 kilometers, where it becomes geostationary, so it rotates at the same speed as Earth, and that's why you can always see it at the same location, and that makes it sort of simple to connect to it, because you always know where it will be based on where it were when you put up your equipment. But then you are very far from Earth. You only need a few of these satellites in order to see the whole Earth, but you also are so far away that you can't really send much data. That's why it has been using for TV broadcasting across the world. But then I think one of the new things that have been happening is that we would like to also do data communications. And of course, over those satellites, you could do some voice communications in the past, but the delays are very large and it's very little capacity, so it's so expensive technologies. But the new thing is to send up satellites that are much closer to Earth in what is called a low Earth orbit.
So that's the LEO, right? So there's a GEO for geostationary and the LEO for low Earth orbit. And
exactly.
The GEO are like stationary relative to Earth. So if you have like a dish antenna, you can just point it and you never need to adjust its direction.
Yes, exactly.
But for the LEOs, they are much closer, so they move much faster. So you actually need to track them. You said the GEOs are like, you said 36,000 kilometers.
Yes.
So that's quite far. I mean, the radius of Earth is about 6,000. So it's like 6 times as far out in there's no atmosphere. I mean, there's just space, just vacuum. And but the LEOs are much closer, yeah.
Yeah, do you know where the space starts? Trick question.
Yeah. I mean, it cuts gradually, right?
Exactly. So people are trying to make definition of this, and I think whenever there's now these commercial flights that are meant to bring people to space for a few seconds or minutes, then they have been arguing about where we should actually put the line for where space starts. But typically that is at 100 kilometers above Earth, and then normal aircrafts are at 10 kilometers, so
it's like 10 times. But the LEOs are much closer.
I mean, in principle, the orbit that we called LEO starts where space starts, and then it goes up to 2,000 kilometers, and above that, you have something called the medium orbit, that is between 2,000 up until this geostationary point, and there you need to build your satellites in different ways because you get exposed to radiation in a different manner. So the attractive thing is these shorter distances. These ISS, International Space Station, is at 400 kilometers, and I think the satellites that we will be talking about are more between 500 and 1,000 or 1,500 kilometers above Earth.
Right, so we're talking really long distances here. So, but I mean, to break this down, so radius of Earth 6,000 kilometers, and the geostationaries are out at 36,000, and the space starts at 100 kilometers from surface, and the LEO orbits are from like 100, you said, up to 1,000 kilometers. Was that accurate? Yeah, okay, a lot of zeros here
exactly.
To keep track of.
As you were saying, at the geostationary point, the satellites are not moving with respect to our viewpoint. Of course, they rotate together with Earth.
No.
But at these LEO satellite orbits, they typically moves 8 kilometers per second.
8 kilometers per second.
So they rotate really rapidly,
Yeah, that's really rapid. I mean, because if you think of like a human walking, it would be maybe a few meters per second, and then we're talking kilometers per second. So
yeah, I mean, 8 kilometers per hour isn't much, but per second is really a lot, right?
3,600 times faster, yeah. So how many satellites do you need to establish any kind of reasonable coverage in these orbits?
So if you start at the geostationary, I mean, you typically need some 3 to 5 of them to see the Earth from some different angles, so you can cover the entire Earth. And so that's not very much. For the LEO satellites, in principle, if you just want to see the entire Earth, you should need some 30 of them or so. But then every point you would only be able to see one at a time, and you will still have large fluctuations between if you have them above you or if you have it far at some angle. So therefore, the new operators that are sending up LEO satellites to try to provide data communication over the Earth, they are targeting a few thousand satellites.
That's a lot. Thousands of satellites orbiting in this LEO orbit. I mean, of course, there's a lot of space there, so the risk that they would like collide, I guess, is minuscule, next to zero. But still, 1,000 is a lot.
Yeah, I mean, they are not colliding with each other typically because you can control them also and push them a little bit in their orbit, so they should stay where they are. But there is certainly some concerns about space debris, that other objects around there and that they might be heading towards satellites, and that you will need to be able to move the satellites just slightly so they are missing. So there are certainly concerns about if we're sending up a lot of satellites into orbit, will we eventually make a mess out of those places?
Yeah, will they eventually be too crowded? Because these guys stay like at the regular orbits, and then of course if the orbits are calibrated so that they nearly intersect, and But I mean, the number of satellites you need, I suppose, also would depend on the beam width when you actually listen and transmit, right? Because if you could form very shallow or very narrow beams, then you would need like more of them to cover. But if you would use broader beams, then you could get away with fewer. So it sounded like the number you mentioned, like 1,000, is more like a commercial kind of decision rather than some fundamental limit, or
exactly. The fundamental limit is that you need 30, and then they chose to have a bigger one in order to have more satellites visible at any point, and then try to provide more consistency in that there should always be one that are sufficiently close above you in order to provide some service. And then of course the hardware that you have on that satellite needs to be able to form signals that are covering only a particular piece of Earth, the one where you are supposed to provide service quality. So the more satellites you send up there, the more you need the transmissions to be narrow down to Earth. So you sort of let the satellite, if you have 1,001, you want to divide Earth into 1,000 pieces and then cover each one of them with one of the satellites. And the more you send up, the more narrow the transmissions needs to be.
Yeah, got it. Okay, so 30 to really cover the entire Earth, but in practice you need like 1,000 or so, because you're forming narrower beams and smaller spots on the surface.
Yeah.
So, but now, so we got these LEOs at like 100 to 1,000 kilometers, and now we got the GEOs at 36 36,000. So is there like anything in between of these orbits, like more slow moving but still not stationary satellites?
Yeah, there is a lot of different types of satellites for space observation and things like this. But I think in our context, the most important thing that you find in between there is this so-called GNSS. Satellites are used for global navigation systems, and a typical thing that people usually say is GPS as such a system.
Yeah, so all the GPS and all the other satellite navigation systems, they are like in between them there. So do you know the exact like altitude of their orbit for the GPS satellites?
No, I don't remember that, and I mean there are a few different ones. GPS is the American ones. There's Galileo in Europe. There's GLONASS in Russia, and there's some Chinese version as well. So I don't remember the exact numbers there. But what I know is that they typically target to have around 30 of those satellites, so you'll be able to see a couple of them at the same time, and then you use that to localize yourself, and also you can get time synchronization information from them as well, so you know where you are and what time it is. And
that's right. I mean, so and they move relatively slowly, so they are probably a bit up.
Yes, exactly.
So now talking about these LEOs, I mean, of course, for the geostationary satellites, we just use like a fixed dish antenna that points in a fixed direction. But for the LEOs, they move pretty fast, so we would have to track. How would this work? I mean, would you have like an antenna that you physically track, or would you have a phased array of some sort to track them when they move across the sky?
Right, yes. Then we really come into the kind of antenna array technologies that we have been working on ourselves. So in principle, you could, of course, have such a dish antenna, and then you mechanically move it back and forth and tilt it towards the satellite. But that is not very efficient to do, particularly when you need to move relatively quickly.
No.
And when you need to sort of jump quickly from one end, you have one satellite in to the right, and then you quickly, when it goes out of your sight, you want to jump to the other side and find another one who's coming along the same trajectory. Then that is not very efficient. So that's why phased arrays, so antenna arrays that can phase shift the signal, so you electronically can steer your view and transmissions at different angles. That is ideal in these cases.
Right. And when you steer this antenna array, I mean, as always, when we work with antenna arrays, we need channel state information so that we know where to point the beam. But here, I suppose, because these trajectories, when the satellites are orbiting around the Earth, they are controllable and deterministic, and therefore completely predictable. So in principle, you would know, if you know the exact what time it is, you could compute where are the satellites located, and then compute how the array should be configured. Is that how this works, or is there some kind of other pilot exchange or anything going on?
No, this is the main thing there, and that's why we also mentioned the GPS systems, because you can use them to get the time synchronization and localize where your receiver is on the ground, and then you combine that information with information about how the trajectories of the satellite are to calculate where you're supposed to have this satellite, and then you can tune your phased array to point in the right direction. If that information isn't reliable enough, of course, you could have to start to go around and search around with beams as well, as you would be doing on Earth. And there are attempts of trying to be not so reliant on the GPS systems anymore, because, they are far up, they work, but they are easy to jam in certain situations. So there is a hope that you could do something similar without being reliant on those systems as well in the future.
Right, got it. So basically using GPS to distill the position and the timing, and then mapping that information onto where are these LEO satellites so that you can point your beam in the right direction. But of course that relies on using the GPS then, which is, as you said, very susceptible to jamming, for example, because the receive power levels are so small. But also when these LEOs move, they move quite fast. So isn't there going to be like a lot of Doppler shifts in the signals that we need to take care of?
Yes, definitely, that is going to be the case. So it can certainly be so that these variations in angle that we describe for the beams, even if the satellites are moving at some 8 kilometers per second, what matters is really how the angular velocity is changing, and that one can still be manageable. But one of the big things when an object moves quickly while communicating is that you get this Doppler effect, and depending on if the satellite moves towards you or away from you, the frequency will increase or decrease, and that is an issue then that needs to be dealt with in the systems.
Yeah. So how is this dealt with the Doppler shifts?
So if you go into academic literature, a lot of those are talking about different types of waveforms and how you can design waveforms that are more sort of robust against these kind of issues. So the typical thing we are using today is OFDM systems, with you divide your frequency domain into different subcarriers that carries the data. They are orthogonal, and then when they get shifted, then that orthogonality is broken, and therefore people are talking about there are other kinds of waveforms. We mentioned some of them in our sensing episode as well, OTFS, AFDM, and so on. But if you actually go into the system that I use today, the first thing they are doing is to do some kind of compensation for the Doppler shift. You shift it in the opposite direction before transmission so that it will be shifted in the right way at the receiver and come back again.
Yeah, I mean, I was just going to say, why does it matter what waveform you use? If the Doppler is known and predictable, you can just compensate for it. It's basically taking your signal and pre-multiplying it with e to the j theta of t, where theta of t is a known function, right? You could compute based on your location and the timestamp. So it doesn't sound to me like it would make a big difference. That the waveform choice of waveform should be made based upon Doppler considerations primarily.
No, I mean, it becomes some kind of trade-off there between engineering solutions and some kind of theoretical ideas about how we should build the systems, because the practical systems are using OFDM and do pre-compensations, and it apparently works. We have commercial systems, right?
I mean, to me, that sounds like kind of the natural solution. Of course, OFDM comes with its peak to average ratio, and I suppose in satellites you have very limited availability of power, so power efficiency of the amplifiers might be a significant consideration, but apart from that, it seems hard to find any arguments against using OFDM, and just given that you can pre-compensate for the Doppler accurately enough, I mean, that shouldn't be an issue.
Yeah, and I think that is the key thing there, accurate enough, because you're totally right that if you have a perfect ability to predict your Doppler, you know everything about how they are moving towards each other, then you can do a perfect compensation. It doesn't matter. But as soon as you have some error in that one, then different waveforms will have different susceptibility to that issues. And that is why people are arguing that other waveforms would be better somehow.
Oh, that's totally true. I mean, but you, on the other hand, is still a fairly slow process in that there might be a Doppler shift, and that Doppler shift as a frequency offset, I mean, might be changing over time, but it probably could be tracked and even predicted with very good accuracy, so that irrespective of what waveform you use, you can still get by with that. So how are these networks organized and how do they operate? I mean, for example, if we are using a satellite terminal to communicate over the internet, how does the data find its way? I mean, I understand that from the terminal to the satellite, there is a radio frequency link that we just talked about with beamforming and so on. But then what happens next?
Right, exactly. So we have talked so far about the terminal connecting to a satellite, and you have a constellation of them that is flying over different orbits. They are circling like different ways around the globe in different directions and so on. And then those satellites then needs to be connecting back to Earth in order to connect to the rest of the internet. And then we have something called ground stations that are at fixed locations on Earth that you put them out in order to communicate with satellites. And we typically have fewer ground stations than we have LEO satellites. So areas, if you take a Starlink system, which is a US-based system, I think there they might have a ground station in each American state. But in Europe, you have just a few of them that is then connected to the satellite. So then if you send your data from your terminal up to the satellite, then the satellite either sees the ground station directly and sends a beam towards that one with the data, or it needs to send it between different satellites. So you route it in the sky between the satellites to one that can reach down towards the satellite, to the ground station and send it down there.
So do you mean that every ground station communicates with several satellites at the same time then? I mean, if there are fewer ground stations, that's got to be the case, right? Or is there some kind of...
It can communicate with multiple satellites, and it could also be so that the satellite is sort of in the sky gathering the data together and send it just for a few smaller number of them as well. So the system typically have antennas that are pointing between each other in the orbits, so that you can sort of, it's like a multi-jump system between.
No, I see. So are you saying that the satellites in among themselves actually form like a mesh network?
Exactly.
So that one satellite might be receiving, let's say I'm transmitting something, some satellite might be receiving, and then that satellite determines that, hey, there is no ground station in sight. I'm going to ship this data, hop it over to a neighboring satellite, and maybe that satellite could see the ground station.
Exactly.
So there must be like a very advanced relaying network that operates up there. I can imagine it must be very difficult to optimize how to best route all these packets.
Exactly. So people like you and me who have been working a lot on the physical layer, we might be interested in the links that you send from the ground up to the sky or so. But people who are working on higher layers in the protocol stack, they are working particular with how should this routing be done in an efficient manner.
Oh, I mean, that sounds like a super important problem that we should also be interested in. And maybe it has been solved, I don't know, because these systems are out there and operating. So.
Right, but I mean, people who are then envisioning future systems, they're also considering maybe we should put some specific intelligence in the sky as well. I think Elon Musk has been talking about putting sort of computing places at some satellites around there, and then of course you need to route the data between the satellites until it reaches the server in the space, and then you compute things and send them back. So you can make the system very complex if you want to. You can also try to make the system as simple in space as possible. So try to put everything down in the ground station, in the sense then that you might be preparing the entire signal to be sent to the users at the ground station. You'd even do the Doppler compensation or so. You send it up to the satellite, and it's only amplify and forward it downwards. So there are different ways of organizing this. Or you treat this as multi-hop systems where you send some data up to the satellite, it decodes it, and then decides on how to transmit down. So you can put different kind of functionalities in the satellites.
Yeah, I see. So do you know what kind of relaying is being used when they communicate between satellites? I mean, when the data are relayed, this has happened through amplifying forward or decoding forward or something else?
Right. I would say that this is often proprietary solutions, so they are not really sharing that, but the discussions are definitely about using one of those different kind of protocols. And sometimes people talk about the bent pipe, which means that you want to just create like one continuous channel from the ground station up to satellites, maybe across a few satellites and then down again, and then it's like an amplify and forward kind of protocol that goes up and down.
Right. So the bent pipe is like a kind of data goes up the satellite, over to another satellite, over to another satellite, and then down to the ground station somewhere.
Exactly.
That's kind of neat, yeah. But I mean, it's kind of interesting because the sort of mesh networking, I think it was popular to consider for terrestrial radio for a long time ago, probably 25 years ago, but it never really became a big thing. But for satellites, you really need it. So that's an interesting observation. So what spectrum bands are we operating in here?
Right. So that can be many different things, just as on the ground. And it, I think, depends on what kind of use cases you are considering and also what spectrum happens to be available. So there are some systems that tries to connect to smaller devices, and I think we will come back more to that later on. And they are working around 2 gigahertz at frequencies that we are often using today on Earth for communication with mobile phones and so on. But these dedicated systems that have a terminal on the ground that is transmitting and that is connected to the power grid and can be big and have this phased array, they might be communicating at 10, 12 gigahertz, for example. And there are some systems that go all the way up to 40 or 60 gigahertz.
So the span of frequencies used, so now we're talking about ground station to satellite. That span of frequencies being used there is quite large.
If you take the ground station case there, I think that is where you really have the opportunity of having advanced hardware at both the ground and in the satellite. So there you can sort of aim towards using higher frequencies for those aspects, because you might have worse propagation condition, but you can build a bigger antenna or use more power. While when you connect to your devices, my answer was more about those ones. So some 10, 12 gigahertz for Starlink terminals and 2 gigahertz if you are connecting more directly towards smaller devices.
Oh, right, I see. But at any rate, I mean, there's quite a wide variety of different bands that are used for the actual air interface. So, I mean, what kind of antennas would the ground stations and the user terminals be using here?
Right, so this also depends on what we want to achieve. So, I mean, one very basic type of service is that many mobile phones today, for example, if you have an iPhone 14 or later, you can send emergency text messages to satellites. And that is a system called Globalstar. They have a few satellites around the Earth in the LEO satellite orbits. They're using some 2 gigahertz or so. And then you use basically an unmodified iPhone with a new chipset that can handle this type of things. And then you use the basic antenna that you have there, which is not directive at all, and then you have a strong gain at the satellite. And if you compare this with like a real dedicated system with a dedicated terminal, well, then you, for example, the Starlink terminals, you typically have some 30, 35 dBi antennas, which is like focusing 1,000 or 2,000 times towards one direction, towards the satellite, and you have the similar thing in the sky focusing down towards the user.
So you need really high gain antennas in general, I mean, to get a decent link budget.
Yeah, if you can.
I mean, that's always the case in wireless comms, but here the distances are so large that on the other hand, I mean, you got line of sight all the time, so there is no fading, there is no shadowing or blocking or anything, and just...
Right. So one can basically break this down then for users who wants to use this technology. That one thing is that you use the satellite link as a backhaul link for your network. So if you live out in the countryside, you might be connecting your house to satellite, and then you have a Wi-Fi in your home. And telecom operators that upgrade their networks and want to provide data services and using their cellular networks in the countryside, they might connect their base station site towards the satellite as a backhaul option, but they still want the customers to connect directly to the cell tower. But then, of course, you can also have user devices that people are actually using with their hands that connects directly to the sky as well. And then, it's different kind of use cases, right?
Yeah, quite amazing. So to what extent are these technologies being integrated into the standards? I'm thinking of 3GPP and the forthcoming 6G standard in particular.
That's a good question. So a lot of work has been done on this aspect. So already for 5G, there have been fine-tuning of the standard that is happening, and there is a goal for 6G to take this even further and sort of have something that would work well for both communication on the ground and in space. But these systems that are being created now, and one might read news about that in some different countries users can soon start to connect directly to satellites. They call it direct to device, direct to cell. They are not actually following the standard exactly. They are more sort of doing an engineering solution on top of it. So it's like when you move out of the city and you lose connections to your normal cell tower, you happen to get a signal from a base station that happens to be in the sky. And then that one is pretending to the extent possible to be a normal base station by compensating for the Doppler and these type of things, so the user device doesn't need to do it. It doesn't have to modify things.
So this comes. So are you saying that this comes completely transparently to the terminal? I mean, the user might not even know that it's connecting to a satellite.
Yeah, that is one of
the like goals. Data roaming. I mean, it's kind of roaming then. So you gotta. How can you? I mean, it sounds like dangerous, because if you got your data roaming turned on and then suddenly you're in a coverage hole from your operator and the phone picks up the satellite, then you might not even know that you're communicating over this link.
Right. So then it needs to somehow be built a business case around it. So one thing would of course be that you would buy a subscription directly from the satellite providers. We haven't come to that point, but rather that there are a few countries where some operators locally have teamed up with, say, Starlink in order to be providing those services. So either they are borrowing some of their spectrum that they have on the ground and let the Starlink satellites use those ones to communicate with the users in the country, or you switch to a similar frequency that the user device can still handle, but it is only used by the satellites, and you can connect to those ones. But then, of course, you need those things to work transparently, so you need the handover between them needs to work out well, right?
That's right. I mean, it sounds like a complicated handover problem to hand off from a terrestrial tower onto a satellite network.
Right.
But of course, it doesn't need to happen. It only happens like very infrequently, obviously. It seems more of a difficult problem within the satellite network itself, where you need to hand over between different satellites probably all the time, because these guys are moving so fast.
Yeah, and I mean, the principle becomes a bit different than that on cellular on the ground. You need to hand over to another cell tower because you as a user is driving out of one cell coverage into another one, but you can stay still on the Earth, and then the satellite is passing above you, so the handover is happening in a different manner there, of course.
Yeah.
But then if you look into the standardization, the idea is to standardize features that would make this not only to be like a fake engineering solution that makes it work but not ideal, but actually to introduce some important features into every mobile phone so they can handle this a bit better. You should, for example, maybe to do some pre-compensation for Doppler in the user device, or you should tune your scheduling protocol so you can handle the longer delays you should expect in these type of situations, and maybe remove this reliance on synchronization from GPS and things like this.
Right, but I mean, those sound like problems that could be solved, right, using appropriate technology. But I'm still a little concerned about the link budget, because they were really fighting physics.
Yeah.
Now, if we think terrestrial radio, then tens of kilometers isn't the problem in terms of distance between a mobile terminal and a base station. We've been doing for decades. I mean, even the GSM system had a range of more than, I think, 30 kilometers or something in its nominal version. But these LEOs are much further away. You mentioned earlier 1,000 kilometers. So at the end of the day, we are going to need large antenna apertures, because the only way of overcoming path loss is through an increased antenna gain. And the only way of getting an antenna gain is to increase the physical size of the aperture.
Right. Or at least to make sure that it looks bigger. So you basically have these two different things. You can move the satellite a little bit closer to Earth, and you can make the satellites bigger. And both of these things are being considered now, because as you were saying, if you would go from a mobile phone, or rather from a typical terminal which has some 35 dBi antenna to a mobile phone that has like 0 dBi, you lose 1,000 times in the link budget. So how do you compensate for that? Well, you move the satellites a little bit closer to Earth and you make them bigger. And this is happening right now.
No, okay, got it. But I mean, well, I of course agree. I mean, making the satellite bigger, then you're increasing the aperture of the antenna, right? And if you move it closer, you're reducing the distance. So by doing both, you would of course improve the link budget, but we're still talking about quite long distances.
Definitely.
On the other hand, we got line of sight.
Yeah,
which we very rarely have in terrestrial radio when we are at some distance, at least from the tower.
No, so the companies who are working on this, they are of course fully aware of this physics and are taking steps in these directions. So a satellite of today that are used, still taking Starlink as an example, their version 2 satellites. Roughly, the array would be some 2 by 2 meters, give or take, and then you have big solar panels on the sides that makes it some 10 meters or so long in order to collect the power that you need to run it. But they have designed the version 3, which be substantially larger, and there's also another company called AST Space Mobile that have built arrays that are roughly like 20 by 20 meters. So
20 by 20, because that was my next question. I mean, following up on this issue with the link budget, how large apertures or antenna arrays are we actually talking about here? Now we said 20 by 20 meters. It's like half of it. So let's see, a soccer field is like 50 by 100, and so it's quite sizable, 20 by 20.
You know, so if people want to see how it looks like, Google on AST Space Mobile, and there is a nice picture with people standing next to how the array is supposed to look like. But then you come, of course, into the difficulty, how do you send this kind of things to space? One of the things that has made the whole LEO satellite business interesting now is that commercial rockets to send up things to these orbits have become so much cheaper. For example, the Falcon 7 rockets, so that there is much more economy in doing this type of things. But when you start to build such big satellites, you have a difficulty in fitting them into the existing ones. So as far as I understood, the new Starlink version 3 that have this kind of dimensions, they need to be sent up with their bigger rockets, the Starship.
I can imagine these antennas could also be folded into a more compact shape, and then they kind of unfolds like you open an umbrella once you're up there, right?
That's definitely how it's done. But the claims are that if you would connect a device today in the best situations, you could get some 5 megabit per second. If you like give them all the spectrum, but with these bigger ones you should be able to have 100 megabit per second to use a device, a 6G phone, for example.
That's a lot. I mean, 100 megabit per second, because now we're really talking about satellite. I suppose would never become like the main mode of connectivity. It would become a supplementary mode of access where you can connect when you don't have coverage from your terrestrial system, and then you might not need 100 megabit per second. I mean, you might just need to send some small messages to tell that you're out there.
Right. But the issue then is, of course, that this 100 megabits needs to be shared across users, as you were saying. And
sure.
And that might not be a problem if you have a bunch of people who are skiing somewhere and listen to music while skiing or whatever they might do, or walk around in the woods or so on. But an issue is certainly if you think that you should use this in urban areas, then maybe not, because we talked about earlier that every satellite is covering a particular area, and actually that area that it covers is divided into sub areas called spot beams. So a typical satellite of today is generating some 40 different spot beams in a pattern, and then each one of them have a diameter today of some 50 kilometers or so. So that is still bigger than the cells we have in cellular networks of today.
Oh, a lot bigger.
Exactly.
Right. So, But that basically limits, like, so are you saying that within every spot like that, you could get this 100 megabit?
Yes.
So that gives you like the area coverage or area bit rate. Is there such a thing like bits per second and square kilometer?
Exactly. So it's more than that. If there is one house per square kilometer, well, then you need to divide this 100 megabits with
over the 50 kilometer radius, then into square kilometer cells. Got that. So of course it'll be difficult to deliver like very high capacity to a lot of users simultaneously, but still the peak rates that you mentioned here are really impressive, I think, considering the long distance up to these orbits.
Right.
But in addition to, I mean, limitations on data rates when you got a lot of users, I suppose there will also be high latency of the transmission, no?
Yeah, exactly. So the latency that are delivered, for example, in the Starlink systems seems to be ranging between 20 and 60 milliseconds. At least this is what they are claiming if one is trying to buy their services. And this varies between different countries because where is the ground station? Well, that is having some impact on these aspects.
That's right. I mean, it's not only the propagation delay up to the satellite and then through the mesh network among the satellites and down to the ground station, but it's also the propagation from wherever you're located to the ground station itself. And all these add up in the end. So
exactly. So that's one of the good things with the LEO satellite. They are actually not that far up compared to the speed of light. So it's only some 5-10 milliseconds of delay in order to go sort of one way from Earth up to space and then down again. If you take the round trip delay, of course, you need to double that. But a large portion of this maximum delay is the processing delay at every node along the way as well, and the routing on the Earth from the ground station to the place where you are extracting the data from.
Yeah, I can imagine. So say again, what kind of latencies are advertised? Or if you take commercially operating systems, what kind of latency?
20 to 60 milliseconds.
20 to 60 milliseconds, which is still large enough that you would notice it if you have, for example, a phone conversation over that network. So maybe returning to this question on frequencies, you mentioned earlier that from a device to a satellite, you're operating at maybe 2 gigahertz. Why? Because of then the effective area of an antenna, is reasonably large. It probably helps the link budget to be at low frequencies, I suppose. And you don't need to build like antenna arrays with a lot of elements and phase steering and so on.
Yeah, I think these are the very common frequency bands in 4G systems in particular. So there is some bands around 2 and some around 2.5 that has been used a lot on Earth for these perspectives. And you won't get gigabit per second over those ones, but you might have some 20, 40 megahertz of spectrum there, and that can be used then to boost up your data rate to the numbers we talked about.
Right, so you're saying that at those bands, the wavelength is still large enough that we can get a decent link budget without using phased arrays with a lot of elements.
Yeah.
And we still got, and the frequency is still high enough that we got enough spectrum for the applications that we want. But for the other links, like among the satellites themselves and from satellites down to the ground station, I thought you mentioned earlier that for those links, higher carrier frequencies are used. Is that so?
Yes. So 10-12 gigahertz is typical ones between the Starlink terminal and the sky, and then there are also additional links at 40 gigahertz or even going upwards.
Even upwards.
Yeah.
So is there a limit on how high you could go? Because if you could build with advanced beam steering technology, you could go up even to terahertz, I suppose. Is that feasible, or is there like a practical limit?
The classical sort of name satellite bands that have different letters letters like L, S, C, K, U, K, A, and so on, those bands are typically going up into the millimeter wave spectrum up to some 60 gigahertz or so. But people are also considering sub-terahertz and terahertz communication, so above 100 gigahertz of, because you have abundance of spectrum there, but of course you need to get the link budget together.
Yeah, I mean, that's the point, right? The spectrum is for free, but the link budget gets tougher and tougher unless you build really very dense phase-controlled arrays with a lot of elements. And I suppose there might also be some sub-bands where moisture in the atmosphere or rain, for example, would attenuate the signal a lot. So
you definitely have that issue. And then between the satellites, you are in a different situation, because then, I mean, we know when we are flying an airplane that once you come up to the cruising altitude, you are typically above the clouds. And
that's right.
In the same way, then the satellites are far above the clouds, so there you don't have the same kind of issues, which means that...
No, but I meant from the ground station and up to the satellite, you might be affected by weather, right? But of course, between two satellites, there is no atmosphere, so...
Yeah, no. So some of these satellites now that are creating this kind of routing network that we talked about, they are using optical frequencies to send these signals to each other. And I think some of the people who are then doing research on maybe we could do something in between optical and 2 gigahertz, these sub-terahertz or terahertz frequencies, their selling argument would be, what if we can find some ideal frequency that we can use both between satellites and down to the Earth and use the same one and simplify?
Down to the ground station. That's quite interesting. I mean, but aren't a lot of devices available, right, for transmission and reception in between of the sub-terahertz and up to the visible optics band, as I have understood?
No, exactly. And this is, of course, one of the selling arguments to do this direct-to-device thing at 2 gigahertz, because if you can only do some minor changes in the chipsets for all the mobile phones across the world, and then all of a sudden they are all capable of connecting to the sky, well, then that is a much more important thing than putting in a special radio that only gives you space access. I mean, we saw this whole thing with the millimeter wave business in 5G as well, that there are some dedicated phones, you can buy them in the US and a few other countries that have a special transceiver for the millimeter wave band, but they only used in a few countries, so people don't want to pay extra to buy it, except if they live in those countries.
No, I definitely can see that. So now we spoke about beamforming, but beamforming so far has meant, to my understanding, that we basically got a phased array and we point it in like different directions in elevation and azimuth. So can any more advanced MIMO processing be used, like by the devices themselves or by the satellites or by the ground station? Or could you do like MIMO at the satellite or distributed MIMO between different satellites, for example? Is that feasible, or is that already being done in some form?
People have been exploring this for a while, and this is, of course, also what my personal interests are in when I've been entering this research field last year. So there are these other features that we typically associate with MIMO, in addition to beamforming. And we have spatial diversity and spatial multiplexing as these two different features. And if one thinks about spatial diversity kind of thing, what would that mean? Well, that normally means that you want signals to come from different paths so that you can utilize that maybe some of them are occasionally blocked or so on. And the way we typically have organized these satellite networks in the past is that, you send them up, each of them are creating some tenths of spot beams, but those beams are non-overlapping. But of course, if you have 1,000 satellites up in the sky, but you only need 30 of them to cover Earth, every user device will see multiple of them. And should then, if you have an antenna array in your user device, you can do digital beamforming in order to jump between them quickly to pick the fastest one, or deal with blockages of them, or you could actually do spatial multiplexing, meaning that you would get different streams of data from multiple satellites down to the user device.
Right. Right. Sounds like, I mean, conceptually, a lot of what we know and have developed for cell-free and distributed massive MIMO could be applied also to satellites. An obvious challenge seems to me to be able to phase synchronize these transmitters and, of course, getting accurate channel state information. I mean, conceptually, the challenges are not much different from what they would be in terrestrial radio, because we still have mostly linear time invariant. Well, there's a lot of Doppler, but again, they can be compensated for, right? So we got like mostly linear time invariant channels, and we would need to identify those channels either by knowing what physical directions that we got these different satellites in, or by inquiring channel state information by sending pilots and so on. So sounds like an interesting and ripe ground for research.
Right. Yeah, one of the challenges there, I think, is that even if you could synchronize them perfectly with each other and the orbits would be perfectly deterministic, of course in practice they are fluctuating a bit back and forth, then an issue is typically that you use OFDM, and in OFDM you have this cyclic prefix that is meant to deal with your variations in propagation delays between different paths. And if you now are operating and do distributed MIMO on the ground, then typically the base station that connects to you, they might be some hundreds of meters apart have that as a delay difference. But in Earth, when you are at the 1,000 kilometers altitude, and then some of them are above you at 1,000 kilometers, some of them are further towards the edge, then there will be kilometer-wise differences in propagation delays. And
but that's that's a really interesting point. I mean, so to deal with that, you would need really huge cyclic prefix, and then in order not to lose too much of efficiency, you would need really long symbols, I suppose. Otherwise, because the cyclic prefix would eat up the efficiency. Now, obviously, one could also use other transmission technology. This might be a reason, in fact, to step away from OFDM with a cyclic prefix and use other types of modulation formats.
Yeah, no, and what we have been exploring then would be that let's not try to send it phase coherently with this particular way, but instead view it as the user device will see the satellite at substantially different angles. What if it just sends different streams of data from those satellites to the user? So they take the chunk of data you want to have, you cut into two pieces, send them from different directions. You use the digital beamforming capability in the mobile phone to decode one, treat the other as interference, and then you swap like this, and then you would simplify the system.
I mean, but this of course can be done also in terrestrial DMIMO, right? You got different access points sending just different data streams, and then at the receiver you got an antenna array, and you run your zero forcing or whatever beamformer to resolve these streams. Which in terrestrial DMIMO we experimented also a bit with that. It works so, but maybe for the satellite scenario it might work better.
Yeah, you need this the channel to different transmitters to be sufficiently different so you don't get much interference.
Different, right? Otherwise you'll amplify noise too much when you separate them in your zero forcing decoder, and then performance is going to break down. So
line of sight transmissions with satellite with sufficient angular separation should provide you with relatively good channels for those perspectives.
That's right. I mean, that sounds like a scenario where this would actually work pretty well. So that's an interesting point.
Yeah.
So what is the time frame of these developments, and when would we expect? I mean, the technology is out there, but for example, what we talked about now, using satellites acting as a MIMO constellation or a MIMO transmitter, when do you expect that we will be seeing that in commercial operation?
So these things basically happens as we speak. So there are companies that are already talking about that we will soon launch this service direct to device from satellites, but with the old satellites where you just get a relatively low data speed. They are teaming up with satellite providers for that viewpoint. And then you have the sort of the long time frame thing where 6G standardization happens and new features happening there, and then that will be launched more towards the beginning of next decade, I think. But in between there, you have these bigger satellites that we talked about, and they are allegedly being sent up from right now, and then it might take a while before they are actually sufficiently many, so they will turn on the services. And it's also so that the operators prioritize particular regions of the world. So I was discussing this with the regulator in Sweden, who said that, well, right now, even if the Starlink satellites are sort of in orbits that are not going all the way up towards the north of Sweden, you can use it in the north of Sweden with this kind of basic services. But the new bigger ones, they will not cover more than the lower third of Sweden. So the upper the 2/3 where we have much less population, they will not actually benefit from those services anytime soon.
Oh, I see. Yeah, I mean, there seems to be a little bit of a chicken and egg problem somehow. That, I mean, if the idea is to serve areas where there isn't terrestrial coverage, then those areas aren't likely to be populated by a lot of people, plus that these services are going to be expensive. So I mean, to get satellite coverage, you would need a lot of people who can actually want to pay for the services. But if you have a lot of people who are willing to pay, then they probably have terrestrial access already. So maybe it'd be like on the oceans or somewhere where you just can't build terrestrial access, where satellite becomes really important.
The ocean is certainly one thing. Another thing is that a country like the USA is very wide, and there are people out in the countryside who have good financial situations and are not connected very well, so they are a good market. And also Africa seems to be proceeding as a market, maybe not for direct to device, but direct to cell, sort of help building out their infrastructure. So that is happening.
Yeah, and probably there's no infrastructure, that's right. But I mean, in the US, you're right, some parts of the US are very sparsely populated and might be actually very expensive to build good terrestrial coverage, and satellites would still be competitive. So it seems to me that I'm trying to identify what have been the driving technology forces that have led to this development that we're now seeing with large-scale satellite deployments and these pretty high data rates after all. I mean, and because satellite comms as such has been around for a long time, right? I mean, there were also earlier systems. There was this Inmarsat and others. Is it so that one important enabler is now the availability of relatively low cost launching of rockets, so that it actually became cheap enough to launch a satellite that we can deploy so many of them? I mean, it sounds like that's one fundamental enabler that has really happened.
Yeah.
And maybe another one would be, I'm just speculating a little bit here now. Another one might be, of course, the development of the microelectronics is the sheer fact that you can actually build these large antenna arrays with a power efficiency that's good enough that you can power them using solar that shines and kind of pings on the satellite. Is there any other fundamental enabler that you would identify that has made this development happen right here and now?
No, I think it's primarily those two things combined with that there is a business case where you can make money from particularly countries like the US, where you have a wealthy set of people and you have surprisingly bad coverage in the inner parts of the country.
Right, but that's more like a market argument, right? For why do we need this? Or why do we want this technology? Why would anybody want to have this? Okay, but I'm thinking like fundamental technological enablers. Then it seems like relatively low cost rocket launching technology developed a lot by SpaceX. I mean, of course, and also the development in microelectronics, which, by the way, also has driven a lot of the 5G and 6G and so on for terrestrial. but maybe those are the ones mainly.
Yeah, no, and I was going to say that Starlink, we are talking a lot about them because they are ahead in the race, but there are other companies. So Starlink, they have orbits which are like not equator in this particular way, but a bit inclined, but still they're going like that. Then there is a company like Eutelsat OneWeb, a merger that is going with North and South Pole orbits that goes in different ways. That is more of a European effort, and I think because of the market reason that I mentioned, they have not been investing or is not as far so at this point when it comes to the number of satellites they have in their the constellations. But they are building. There are a few other constellations that are happening. Maybe we'll have 3-4 different satellite constellations, just as we have 3-4 different operators in most countries on Earth. Mm-hmm. And then eventually the satellites are also living for 5-10 years, and then they needs to be removed because they don't function anymore. And that also means that new companies can be sort of catching up.
Right. I mean, that's also an interesting question. What happens to all the decommissioned satellites? Or once they stop functioning, then will they self-destruct and just blow up somehow? Or will they slowly spiral down into the atmosphere and burn? Or will somebody shoot them down with, I don't know, laser or something? Or would you send like in Star Trek? Or no, is it James Bond or Star Trek? I never remember. There's this movie where there's like a big satellite comes and eats a smaller one. Or would it be somebody orbiting around up there and cleaning up? Or
yeah, you don't want to shoot something down because then you create a lot of space debris. But yeah, I mean, either you move them into an orbit where they just continue circling there as garbage and make sure that they're not colliding with each other, or you are doing controlled decommissioning by bringing them down so that they are falling down and burn up. That is what you're going to do.
Burn in the atmosphere. Yeah.
But yeah,
so, I mean, as an interesting thought experiment. Would be, what are the true fundamental limits of satellite access and satellite communications? If we imagine a universe where the cost of launching a satellite is zero, then what would it be like anything like an optimal number of satellites? I mean, at some point they would just get too crowded up there.
Yeah,
they would collide with each other. They would interfere. All these beams would be like, they are still broad enough that there would be too much interference, I suppose. And how will the technology scale? Because if you think of it now, there might be thousands of them in this LEO orbit, but we're talking about huge distances still. So that space is very, very sparsely populated. Is there like I don't expect you to know the answer. I mean, just kind of casting the question very broadly. Is there like an optimal or a fundamental limit on how many satellites could eventually be deployed or be useful? It's a little bit like in MIMO. I mean, there's the limit on how many antennas. If you could build a MIMO array, then we know that 100 antennas is pretty good, but now maybe we can build 1,000. But what if we could build 1 million? Would it actually help us? Or would we hit some fundamental limit somewhere where physics is just against us because coherence isn't enough, or speed of light is too slow or something? Do you know if anybody has in the open literature considered any of these?
No, I haven't seen it specifically.
Directions?
No, not specifically like that. And it's also the question about if you want to increase the number of antennas in space, do you want to do it by taking the satellites you already have and sort of add more antennas to them, or do you want to have more satellites? What is the preferred mix when it comes to those type of things? Right. And are there some kind of when it comes to building a very large satellite, are there some limits where it's not really doable anymore? You can't build large enough solar panels. Are they growing at a faster speed than the array of? So I think there are a number of things there that I'm not really aware of the limits on.
I mean, those are really interesting questions, right? Fundamentally, is it better to have a lot of smaller satellites that can maybe operate phase coherently even together, as compared to having one satellite with a big array antenna? Or another question one could think of is like, what if somebody invented, let's say, a portable nuclear reactor or fusion-powered reactor that could give us energy for free, and small enough that you could actually put it on a satellite, so that we don't have limitations on transmit or like transmit power. There will be limit maybe, but we don't have limitations on power supply. How would that change, if at all? Or what are the fundamental limits for what one could do? Anyways, this becomes a lot of speculation, Emil.
Yeah, and there are certainly open problems to solve, and I'm happy to see that as well, since we are kicking off our activities in our so-called Smart 60Sat Research Center. So,
you got a whole research center.
Yes, we were kicking off recently those type of things. I will put a link to that center and my recent paper about distributed MIMO in space in the description of this episode for people who would like to know more.
Yeah, definitely do that. And I'd really love to come and visit your center, Emil, and see the activities going on there. So it's been a really great learning experience today, I think, Emil. Thank you so much for this discussion. And
yeah, and thank you for all the listeners, particularly those who have listened to every episode. But of course, we are very happy for all the new subscribers who are liking and hitting the bell icon, so they hear when we have our new episodes.
Don't forget to click on the like and subscribe on YouTube. Yes.
Bye-bye.